let's talk about the first isomorphism theorem. We defined the quotient ring and gave an example, basically just Z mod NZ. Z is the ring, NZ is the ideal, and in this case the quotient ring construction just amounts to the construction of the integers mod n, and the operations that we defined amounts to the operations on integer mod n. Before giving more examples, I need to go through this fundamental result, which will be used then to give more examples. And I don't want to review the whole construction again, but I've copied down the summary of the construction on the right hand side, and it's in this slide where we went through, and the corresponding video where we went through the quotient ring construction from scratch. So before working through this one, you want to make sure that you're completely comfortable with this construction of quotient ring here. So what was that? If you give me a ring R and an ideal I, then we defined a new ring called R mod I. The elements of R mod I are the congruence classes mod I, or the cosets mod I. A coset is a subset of R that looks like this: A plus X, where X varies over I for some A in R. That coset is denoted by A plus I. So R mod I is the collection of all these cosets, and on that set there is a new addition and a new multiplication that we defined, and they satisfy these properties. When you add a coset of A and a coset of C, you get the coset of A plus C, and when you multiply coset of A and coset of C, you get the coset of AC, and that holds for all A and C. Further, there is this very important natural surjective ring homomorphism from R to R mod I that takes an element of the ring R to its coset, A plus I. Okay. Now, here's the isomorphism theorem. Let psi from R to S be a surjective ring homomorphism. An on-to ring homomorphism. And let I be the kernel. All the elements of R that go to 0 when you apply psi. Then, here's the conclusion. There exists a unique isomorphism. Isomorphism means ring isomorphism. Call it eta, from the quotient ring R mod I to S, such that eta of a coset of A is equal to psi of A, and this holds for all A in R. In particular, so this is the statement of the theorem, but I want to emphasize something. In particular, what this says is that if you have a surjective ring homomorphism from one ring R to another ring S, then the domain ring modulo the kernel of the homomorphism is isomorphic to the image ring. And this would allow us to identify certain quotient rings with other rings that we have seen. Okay. Let's indicate something about the proof. It's written out in the notes, and I won't have time to go through the whole thing, but let's indicate some of it. The main point is to check that there is such a function. Okay. So you want to define this eta from R mod I. Let's think aloud a little bit before we write formally. You want to define this R mod function from R mod I to S. So you give me a coset, right? That's what an element of R mod I is. It's a coset. And I have to tell you what is eta of that. But actually it tells you what you have to do. A coset does look like this. It's a plus I for some little a in capital A. And then I'm supposed to send that to eta of a. I'm supposed to send it to psi of a. Psi is a well-defined function on R, so if you give me a, I can send it to eta of a. But the problem is that the same coset can be written as a plus I for different a's. You see, all you have to do is you have to choose some element of capital A. If you give me two different elements of capital A, then a plus I and a prime plus I are both same as capital A. And then I'm supposed to send that to psi a prime as well. So I'm in trouble unless these things are equal. So what I need to check is that if you give me any two elements in capital A, psi takes the same value there. So let's just check that first. Let A in R mod I and fix some element in this coset. My claim is that we claim that psi of A is equal to psi of A naught for all A in capital A. So psi takes the same value on all elements of this coset. That's what we needed here. Let me erase this stuff and see why this claim is true. So to prove the claim, note that A is in A. So let's take A in A. Then A and A naught both are in A, in capital A. So the difference, by all the equivalences we did last time, the difference is in the ideal. Two elements are in the same coset if and only if the difference is in the ideal. That was one of the conditions. But what is I? I is the kernel of this map. So the difference is in the kernel. So psi of A minus A naught is 0. That's what being in the kernel means. But psi is a homomorphism, so this is same as psi of A minus psi of A naught. So psi of A is psi of A naught. That was your claim. Okay, that proves the claim. Once you have this, you can make your definition in a straightforward way. Now define eta from R mod I to S as follows. Given some element of R mod I, what would I do? I'll choose an element. Choose A in A and define. So this little a is now an element of the ring, and I can apply psi to it and get an element of S. And I let that be eta of capital A. And the claim we just proved shows that this is well defined. The claim shows this eta is a well-defined function. Because you could choose different little a's, but which one you choose does not matter because the psi a's are all going to be the same, because psi takes the same value on all elements of capital A. That was exactly the claim. And once you have this function, you can also check this key property, this one. Because what is eta of A plus I? Well, to know that, you have to choose an element from this coset. And I know one element of such a coset, namely A. And once you have an element of the coset, you are supposed to apply psi to it. And that's eta of the coset. So from definition of eta, we find that this is true for all A in R, since A is in the coset A plus I. Okay. That's the crux of the matter. Now I have to check that the function that we defined preserves addition and multiplication. It's onto, well, it's onto essentially because psi is onto, and it's 1 to 1. Let's check that it preserves addition, meaning you give me two elements of R mod I need to check that eta of A plus B is eta of A plus eta of B. So to calculate that, I need to choose an element of capital A and an element of capital B. So then A becomes little a plus I, and B is little b plus I for some A, B in R. So then this eta A plus B is same as eta of this coset plus that coset. But the way the coset addition was defined, right here up on the right, underlining now, this is same as A plus C plus I. And then the way eta was defined, right up here, eta of something plus I is psi of that thing. So this is psi of, sorry, not C, it's B. So this will be psi of A plus B. But then psi of A plus B is psi of A plus psi of B. So this is by definition of eta. And this is by definition of the addition on R mod I. And this is since psi is an homomorphism. But psi of A is again same as eta of A plus I, and psi of B is eta of B plus I, again by this thing. Up here, the definition of eta. And maybe I should say star. This is star. And then A plus I is A, and B plus I is B. So this is eta A plus eta B. And similarly, multiplication. So we checked addition, now check multiplication. And finally, let's check its injective. Finally, let A be in the kernel of eta. So the way to check some homomorphism is injective is to check that the kernel is trivial. Okay, so check something in the kernel and choose A in A. Then capital A is the coset of little a. And again by star, eta of A is going to be psi of little a. But look, that's 0, which means what? That's what it means, that capital A is in the kernel of eta, which means psi of A is 0. So little a is in the kernel of psi. But the kernel of psi is what we called I, right? So A is in I, so the capital A is the coset of little a, but since A is in I, this is same as I. So this is the 0 element of R mod I, if you remember. So the kernel of eta is just the 0 element. So eta is injective. Okay? And that's basically the